Okay, welcome to Thermodynamics. Where was I? When we were last Thursday, did I walk through this whole example on the Brayton cycle? Did I get all the way through? Yeah, that's what I'm thinking. I also want to walk through the Rankine and reverse Rankine, which is all the chapter 9. Now that you're experts because you did it in the homework, but I imagine you're maybe relying. Did you discover that we have summaries of this stuff posted in Canvas under like extra materials or whatever they're called, that extra resources? There's a sheet that summarizes all these things. How we take a string of processes and turn them into an engine cycle and can come up with, it's not that they've necessarily, if you built the engine that way, it wouldn't necessarily come out with that exact efficiency, but we can scale it and say, oh, this is all like isentropic processes which aren't real, but we can say that that cycle was, 80% like the one that we analyzed, but the real value in doing this is analyzing it like that. You can find out what's important, and it turns out compression ratio is really what drives the efficiency on a lot of these engines. And for a Brayton cycle, it turns out that the pressure ratio, not compression was about volume, and the pressure ratio is actually about pressure. It has a happy medium where you get more isn't better. Too low of a pressure gets poor output, and too high of a pressure gets poor output. And depending on what you want to do, there's always a happy medium, which engineering is all about optimizing and finding that happy medium. Speaking of homework, the syllabus says Chapter 24 is due tomorrow, and Chapter 9 we slipped to today. I still haven't really finished talking Chapter 9, the examples here. Chapter 24 is definitely like a Monday or beyond. I do want to there's two parts to Chapter 24, and I want one of them turned in before the final and the other one at the final. So, it'll definitely not be tomorrow because we haven't started talking about that. But I wanted to finish. The engine cycles are important, and then Chapter 24, which isn't in it used to be in your book, and then they pulled it out in Infinite Wisdom. Not sure what they were thinking because it's for what we do. It's heating, ventilating, air conditioning, all the stuff that goes into building energy calculations, which are built on all the stuff we're not about engine cycles, but a lot about enthalpy and mass balances and energy balances. Yeah.
So is the lab still due tomorrow?
No, it'll be due the next week.
A week from this Thursday?
Yeah, I mean it shouldn't be a whole lot. I mean, if you sit down and look at it, hopefully it doesn't take you an hour to do it, because you do have a lot of stuff written down. But there's things you have to look up and think about a little bit. It's just a memo. You're welcome to turn it in anytime, no later than next Thursday, which would be the next
Not
lab.
Thanksgiving, but
I'm thinking not Thanksgiving.
okay.
That's what I'm thinking. I won't be here. You can slide it under my door, and I'll come get it on Monday.
The doors will be open.
Yeah, there's that.
Here even.
Maybe you could climb up the wall and slide it through my window.
I'll make sure that happens.
Okay. So, reminding ourselves what went on with Brayton cycle. Because the gas turbine, it starts off as a TS diagram. You compress it isentropically, same entropy, and it goes up to a new temperature because gas gets hot when you compress it. And then you add heat, that's going to increase entropy. And then you have the power turbine. So here's work going in, work in on the compressor, work out from the turbine. and then you cool it back down to the beginning point. That's your exhaust heat. And it kind of looks like this, the way we, but in reality, this doesn't exist. In reality, air comes in and it comes out at some other temperature. So we analyze it. It really comes down to for the isentropic with a pressure ratio, T2 is going to be T1 to the R to the K minus 1 over K. That's our pressure ratio. That tells us the new temperature. If we can chase the temperatures around the cycle, then we can use C sub P times the change in temperature, and that gets us a change in enthalpy. I'm going to assign the lowest value to inlet at 0. Not that it's 0, but that's like my reference, and we build on that. So this is 246.1 kilojoules per kilogram more energy at the end of the compression cycle than it was. So I'm going to, if this is 0, that makes this 246. And then they told us that the entrance to the turbine was 1300 Kelvin. They just question is how much energy does that mean? So, well, we know the pressure is the same there as it was here, so it's a constant pressure and constant pressure process, and we just use ideal gas law to find that number, and that's what we did last time. And then it expands with an isentropic one. The formula looks the same as this, except now it's going from a high pressure to a low pressure, so that the R value is going to, it's 1/8 instead of 8 to 1, it's 1 to 8. So that R value is inverted. And we get a new value. So once we have these values, what I can say is how much work went into the compression is the change in enthalpy, 246.1. That generated the heat, but that's all the work they had to put in. It generated heat and it was work involved, but it's all bundled up in this. So that's how much work the compressor did. How much work, how much heat did we put into it? Well, at that pressure, to get up to this temperature, it needed to be this much enthalpy. So the difference between these two is the heat in. How much work did it do? Any guesses? Where's our turbine in this? Silence. Everybody's afraid. Make up a wild guess. Where's the turbine in all of it? Yeah, between 3 and 4. So this is the inlet to the turbine, and this is the outlet. What happened in the turbine? We lost some energy. Did it just go away? Turned into work. The difference between these two should be how much work the turbine did. When you subtract these two, you get how much work it did, but it had to suck up this much. So subtract that from it, that's the net work. How much energy did you put into it? That was Q in. And now we got an efficiency. So here you can look over the calculations on this stuff, but that's how we got that data, and here's the summary. Q in ended up being something like 800 and almost 849. Q out 441. That's an exhaust. The net work was 848 minus 441. You can either come with that as work net equals Q in minus Q out. The amount of heat you put in minus the amount of exhaust. what the heat that's missing, we're assuming, got turned into work. So that's 406. You can also look at it. Net work is turbine work minus the compressor, which is 652 minus 2 is 46, and you get the same number. It works nicely that way when you're just doing things theoretically. And that being the case, ratio of efficiency of the cycle network is 406. Heat to make it happen was 849. We get about a 48% efficiency for that cycle. The actual machine would be less than that, but that would be sort of a limit based on these conditions. There's also a question that they asked in the example, what's the back work ratio? What does that mean? It's taking almost 38% of the turbine power just to turn the compressor. And if you look at the Brayton cycle definition, you know, they have this ideal, they developed it out of the stuff, the things we were using, and it came out over K times the pressure, blah, 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 but it comes out 44.8. Now, why didn't that come out? Well, I did it. When they do this, they're assuming C sub P is a constant value, and it's using, they call it cold air standard, meaning they use all the data to develop this. Assuming it's all at, if all the numbers I used were at 20 degrees C, all the values, then I believe this number would match. But I was looking at what's the temperature that's actually going on, and I cranked in values that were related to the actual temperatures, average temperature in a particular process, and that's a source of error there. If you just look at Carnot cycle efficiency, it says the best, most perfect engine in the world would get like a totally reversible, all processes kind of would be limited to about 77% efficiency. And nothing, if you get an efficiency that's bigger than one of these, this is a good cross-check, because if the Carnot efficiency, and Carnot efficiency is absolute temperature, doesn't have to be Kelvin, could be Rankine, but it's got to be absolute. That's a limit. If somebody says that's more than that value, then they're blowing smoke, or they don't know how to read, or who knows what it is. It doesn't get there. So that's the thing about the Brayton cycle. Rankine cycle. This is more like what we had on the test. Steam turbine. On a TS diagram, the difference, so you start with liquid water. You pump it up to a high pressure. You add heat until it turns, until it starts to vaporize. It totally vaporizes, and then you heat it up some more. Now you got a high pressure, high temperature vapor, and now you run it through a turbine, and a perfect turbine says it would have the same entropy. It comes down to the saturation pressure that you're dealing with for the water there. This is where the heat comes out. The exhaust is about condensing the steam. Work goes in to the pump. It doesn't really show here because the pump doesn't put any temperature into it, and this is a temperature scale. If this was a pressure scale, you'd see a big bump. If the pump is inefficient, then it will generate some temperature because waste energy, the inefficiencies turn into heat. So we set up the cycle for this. We've been doing this just for the turbine itself. But now we're going to And I like to start with the high, for these high points of the turbine. So high energy point is 0.1 for this one. No good reason for that other than, I don't know, that's what I like. I think your book actually starts the low energy point is the number one. Anyway, what we know is they told us it's 350 degrees C at 3 megapascals, and the pressure at on the condensation side is 75 kilopascals, which is a vacuum. These are absolute pressures, so that's like, it's suction. If you open the valve, it's sucking in because it's less than 100. Based on this and this, we can find this out of the tables because, and with the, if you look for this, you'll find it's in the superheat table. When you find it, this data should show up. What we know for sure is step 3, it's a 75 kilopascals. All these pressure is really what's real, and the temperature kind of jumps around in the phase and all that. But these are all going to be at this pressure. What we don't know for sure is that we know that here we're going to be at the saturation temperature because it's just condensed water at that pressure, and that's the temperature that's, you know, saturation temperature. This is a little bit below atmospheric pressure. This is a little bit below boiling temperature of 100 degrees C. We don't know for sure these are going to be in saturation until, in fact, we don't know anything about this point except in the perfect world, we know that S2S equals S1, isentropic, same entropy. So what's the value for entropy here? It's this value for entropy. And now we go looking for, at this pressure, what state has this entropy? So if you look in superheat tables, you probably see it's not there. So, well, let's look under the pressure table and see where this falls. And it turns out that the value in the tables, we're looking for a value of 6.745. Well, at that pressure, the saturation entropy value for liquid is this, and the entropy value for vapor is that. This is between those two. So it tells me we have to be at that pressure. If we're at that pressure and we're between these two, that says we are a saturated mixture. It's a fog. How thick is the fog? So we do this to find how thick the fog is. Turns out 88.6% or 0.886. It's 88.6 of the way from being liquid to being completely saturated vapor. Saturated vapor, like steam, is clear. You don't see it. It's when it starts condensing, the droplets that are actually liquid, they're suspended in air. That's the fog that you see. So what would you call that? Like, like 11% fog or something. But anyway, but now that we know, so we used entropy to find the quality, and now we use the quality to find the enthalpy. So we use that number here to solve for the enthalpy of an ideal state. And if you do the numbers, you end up with a value of 2403. Got me following so far? This is like what was on the test. Some people struggled with that. I don't blame you, but that's what we're here for. what I'm looking for now is, 2474. How do I find it? Somewhere here I've got the calculation for, where did it go? Oh, here we go. The next thing down there was the actual output. So, actual output, what if it wasn't a perfect turbine? What if it had an isentropic efficiency of 90%? That means that number I just got said that's the floor, that's the most energy it can possibly convert for thermodynamic reasons. That's what entropy is all about. Energy below that doesn't have enough, it can't be converted. It's like the water that comes out of a dam goes down to the river. The river's at a 400-foot elevation, but that doesn't help because the river's there and you can't get more elevation out of it than tailwater rivers. There's a limit. So what does that mean? The efficiency, isentropic efficiency, how much work did you actually get done divided by how much was your limit value, which is H1 minus H2 actual, that's how much work you got done, over H1 minus H2S. That was the one we just calculated. And if you solve this for H2 actual, you get something like this, and you take, there's our 2403 we just found, subtract it from this, take 90% of it, subtract it from the high value, and you get the value of 2474. So that is where this value is coming from. And if I wanted to find out X, I really don't care. I've needed entropy to find this value so I could find that value. I need that value with this one and the efficiency to find this one, if that's what we're looking for. The next thing is state 3. What do we know about state 3? We're told that that whole condenser is at 75 kilopascals. It's at saturation. So it's saturation temperature. We know it's saturated liquid. We can look it right up. What's the HF gets us that value. And then state 4, it's at 3 megapascals. If it's a perfect pump, should put a little S on that. That whole thing, when you calculate pressure times the change in volume, or not pressure, change in pressure times a specific volume calculation. That is the isentropic, that's the actual work that gets done on the fluid, independent of how you get it there. So if it's 100% efficient, what do? You have to do a calculation like how much. This is something that doesn't come off the tables, except you have to find the specific volume of the liquid that you're pumping. So that's going to be at that saturation temperature, the low temp, times the change in volume, 75 kilopascals, which is 75,000 newtons per square meter. But this one is 3 megapascals, so that's the 3 million minus 75,000, and multiply it times this little teeny tiny number, and the total comes out to 3.03 kilojoules per kilogram of work done by the pump. Turbine, the work of the turbine was H1 minus H2S for the ideal turbine. and it did possibly 713 kilojoules per kilogram of work. Rankine's, or the Brayton cycle, what we have, 37% of the turbine in that example went to running the compressor. And in this case, I don't know, what's 3 out of, you know, it's less than 1%, it's not less than 0.5%. That's why we condense the water. It's a lot easier to push something hard than it is to herd the cats of a gas. So the network is the difference between these two, because you had to put 3 in, you got 713 out. The heat in was the difference between the outlet of the pump and the high value of you know, the inlet to the turbine. You get 27, 29 kilojoules per kilogram. So that's your Q in, that's your network, and you get, divide those, you get they're like 26% efficient. If you went through all that and you had the 90% efficient turbine, your efficiency goes from 26% to same process, but now you got a little bit different numbers. You got 23% because of the turbine efficiency. If the pump was like 10% efficient, it wouldn't make a big difference here. But if the turbine's 10% efficient, then that really sucks. So tends to be, you want the pumps to be reliable, low maintenance, put them in, turn them on, and forget about them. The turbine's going to be like the prima donna piece of equipment. So there's a lot of stuff you can do. Things like the Brayton cycle, you can do things to take the exhaust heat and transfer it to the inlet after the compression and save on energy and not bring efficiency up. We didn't do that as an example, but you have all the tools to do that. You just have to mess with it some more. You can save energy and be more efficient that way. And they actually do that on turboprops. On the Rankine cycle, do we have this slide before?
Yes.
No. Yeah, we kind of got through this. On the Rankine cycle, there's some there's real things that happen is going through the boiler, you lose some pressure. And the turbines do have an inefficiency, and this doesn't have an inefficiency, and it takes some pressure to put things through the system. But if you want to increase the efficiency, one way you can do it is make it so that this comes down to a lower energy state, which would mean lowering the saturation pressure, and they do run them at as low as possible as you can get. The pressure still has to be high enough so that you can transfer heat to the environment. So that saturation, they'll do it so the saturation temperature gets down to like 110 degrees Fahrenheit, something like that. Because you can still lose heat to a river or an ocean that way, or air usually. Another way is to make the high temperature point higher, but that you tend to get limited by material properties. At really high pressures, really high temperatures, you start running into those problems. So one of the tricks is take it up to the pressure you can stand, which is the temperature you can stand at a super high pressure, drop it down, but not all the way around. Just drop it down enough with a high pressure turbine and send it back to the boiler and heat it back up. Heat superheated steam back up to a new high point and then come down. And typically, they'll do it 3 times. If you get a high enough pressure here, you can come all the way up, and they'll actually do it as a supercritical, meaning the pressure is higher than the critical point here, so the fluid never really changes phase, it just expands. It's so hot that the molecular motion sort of outruns the surface tension effect. And they're jiggling around so much that you never get a surface on them at those temperatures and pressures. It just expands. And they'll take it up to, and then down and do a medium temp or medium pressure and low pressure turbines. And that's what they call reheat. So you can improve the cycle efficiency doing that. Our example said like 26% or something like that. I think that some of the like coal-fired power plants that are like state-of-the-art might get up to like 42% efficiency, which is about as good as you get. So there's an example. And typically, this high pressure, you can't go to a super high temperature, so you go up to whatever temperature and down, and then do like 2 reheat cycles, and then you can get those. It gets more complicated, and then they also have things where they'll take some of this steam that's leaking, because they'll also have the seals leak. And they'll capture that steam and channel it into feed water, such that, sort of like the reheat on the Brayton cycles, they'll take the steam, and instead of condensing it all, they'll take some of the steam that's at lower pressure, and instead of repressurizing it or whatever, they'll just take it and put it into the pressure over here and bubble it directly into some colder water that's heating up, and it'll dissolve into the water and bring its temperature up. So that's they're called feed water heaters. And plants will have like 10 or 12 or 5 or 6 or 10 levels of feed water heaters. Blah, 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 and stuff. This, you may be seeing this on your test. This is, well, did we ever do this? Did we do it on the last test? I always get mixed up between this class and the other one. This you can chart the whole cycle on here, and you can pull off numbers. You don't need tables. It's not as precise as the tables are, but you generally can get the result to be, within 0.5% if you're careful on this. So what is this? This is the TS diagram, but the thing is, the pressures, this line here is already at 15,000 psi. So you don't really need to take it all the way over here. That's already such a high pressure. The whole refrigerator thing. So we talked about coefficient of performance, and put in work in, and it's going to take heat and pump it from low to a high. But how are we going to do that? So it's the Rankine cycle in reverse. So they literally call it reverse Rankine cycle. It's a vapor compression refrigeration cycle. In this case, we get a fog, and we evaporate it in the evaporator. That's the cold side, to the point where it's saturated vapor, or even maybe superheated a little bit at low temperature. And then we compress it isentropically. This is a CS diagram. Isentropic compression, hopefully same entropy, putting work into it until it gets up to a superheat at a new pressure. And now at that pressure, the saturation temperature is going to be higher than the ambient temperature. And you can reject heat from the high temperature to a low temperature reservoir, the air or water. Whereas this one is the saturation pressure is such that the saturation temperature is below ambient temperature. And heat that's soaking into a box, it's going to be colder than that. It soaks into that, and all the heat flow that's going through the insulation goes to this place, and then we take it out, pump it up, and reject it at a high temperature and high pressure. So superheat here, and then we, so you know that's essentially that's what's going on here. Here's our compressor. Here's the condenser, so it's high temperature condensing superheat vapor at elevated temperature into a liquid. And then the liquid comes through here, and let's see, it goes through here, and up to here is a liquid, and this is an expansion valve. And instead of having a turbine, we just let it go. So there's no work being done, there's no, it's insulated in theory, so there's no heat transfer going on. And what's the same is, you know, goes down to saturated liquid, and then we evaporate it. It's going to have the same enthalpy, not same entropy, same amount of energy at 0.3 as at 0.4. And that's actually pretty real. Same energy. We didn't put any work into it. We insulate it in that process. And what comes in here is a liquid at high pressure, and it shoots through here and becomes a fog at low pressure and low temperature. And then the fog melts away in the evaporator. Energy comes in at low temperatures at the low pressure, and it evaporates. And now we've got a chart that we can use. So the isentropic part is in the compressor. The only way we know the two pressures, and those two pressures are going to dictate saturation temperatures. There's a high pressure that it's high temperature it's condensing at. There's a low pressure it's evaporating. And between states 3 and 4, it's a constant enthalpy. That's the important part of the evaluation. Because it's phase change, we're not using any of those formulas that have exponents to the K, because that's about ideal gas, and it's definitely not ideal gas. So it's all about using the charts again. So you know, here's some of the components. The back of your refrigerator is going to have stuff that gets hot. That's the condenser at high pressure. It comes off of that as a liquid, goes into an expansion valve. In this case, it's an actual expansion valve. Some of the cheap, like Beermeister kind of refrigerators, they literally just put a long tube that's really tiny, and depending on how long you make it, it will hold back the pressure, and it's just a fluid restriction on it. That's really all you need to do. But this one is a temperature compensated expansion valve with, on the back side of this, there's an adjuster. There's like a gasketed cap here. On here you can adjust, like if you want a half ton or 1 ton cooling or whatever for this expansion valve. So that's an adjuster. These aren't adjustable if you just have a capillary tube. Then it goes from there probably into the freezer first, and out of the freezer into the refrigerator, or some refrigerators actually have two different coils. They run the freezer and the refrigerator separately. So here's our example. How's our time? Only a few things we need to know to run the whole cycle. We need to know the high, whoa, wrong one. That's the one we just did. We need to know the high pressure and the low pressure. And if we have a mass flow rate, we can actually do, to find the coefficient performance, that's all we need to do. To find actual power and Q in and Q out, we also need a mass flow rate. How fast is the system? How do we scale it up? Not kilojoules per kilogram, but kilojoules per second. So we have kilograms per second. I'm going to start here because I know at this pressure I'm going to have saturated vapor, and then I'm going to have the same entropy. Find that on the new pressure is, if this is saturated, that's going to be in superheat. And that's going to be a temperature above this saturation. We can pick these 2 points off the tables by knowing the pressure. We know those two. And the enthalpy value from here is the same there. And enthalpy is all we really care about. So we already have 3 out of 4 states from the get-go. And the fourth one is using entropy. So in this case, this is all we knew for sure, but we also know that state 1 in this case is saturated vapor because of the definition of how this ideal cycle is going. So if that's the case and we know this, then it's saturated. It's going to be saturation temperature, entropy, and enthalpy are going to be read straight off the table, H, S, G, and H, G. And then this value for entropy is going to be the same at the new pressure. So based on the data at this value, I found that this value of entropy was between 2 temperatures. Now we're interpolating between, it's above, there was a value where it's above and a value where it was below. And I think those 2 temperatures must have been 30 and 40 degrees. So this is the value for 30 degrees, that's the value for 40 degrees C. And when we do this, we find it's 0.8842 of the way from 30 to 40. So we do that for the H values. Between 30 and 40, there's 40 degrees, there's 30 degrees, 88% of the way, plus the value for 30, you get this value for H. And because it's between 30 and 40, that's 9/10 of the way, so I call it 39 degrees C. If you look on the tables, you'll see where these are coming from. Yeah. Now here's where I calculated 2S. Finding X4 don't really need, but that was the only enthalpy we needed. So now to find the work of the compressor, H2S, that was the output of the compressor, minus H1, the fluid coming in. It's the difference between these two. That's the one we just calculated. This was off the table. It says it did 36 kilojoules per kilogram work. What was the Q in? H1 minus H4, that was the bottom line, the vapor. This is the fog, this is saturated vapor. And the difference between those two is 143. If you want to know the Q out, H2S minus H3, that's on the high temperature side. Taking the superheat and condensing it to a liquid. And so that's off the table. This is the one we just calculated. It's 179.9. Coefficient performance. Remind ourselves of the little drawing here. Q low plus work compressor ought to be Q high, and we've got values for them now. If it's a refrigerator, Q low is what we wanted. Compressor is what it cost us, and the difference, we get a 3.96. If the heat flow on the hot side is what we wanted, then Q high divided by the work of the compressor, we get a 4.96. It's always going to be true that the coefficient performance of a heat pump under the same conditions is going to be coefficient performance of the refrigerator plus 1. Why is that? If the coefficient performance is this divided by this, but then you take this plus that and divide it by that, you're going to always have plus 1 because you're getting the heat equivalent of the work you put into the compressor. So, in this case, last thing, if you take those values and multiply by the max flow rate, you get kilowatts for the compressor, and we can turn that into tons of cooling. So this was a 2-ton example. Okay, that'll do it for today.
Okay, if we just stop breathing. Yeah, really. I feel like we need a better I mean, for me, I'm kind of looking at this like, why?
This part right here just that's like exhaust cycle, right? But like doesn't the exhaust cycle happen during the power stroke as it's going down, so the boat back up and
The strokes aren't related to the work. The other thing, power stroke.
But with the exhaust stroke, the volume be decreasing.
But what you do is you can actually, oh yeah, we'll just tackle Russia. You actually have to solve Russia.
This thing here.
Oh yeah, you always spend.
Between here and here.
Yeah. We don't know.
In the perfect world, this is my Untitled Cycle thing.
Yeah, it's basically
So they're saying we're just kind of close system
So like this real are
So that's the
no, actually, it goes from here and push it out and comes back and goes off. This is just compression, but power stroke. Your exhaust. When you're done with that process.
because I mean we're going through it all.
Yeah, the 4 processes don't match.
That's true.
It's just because they're 4, they're not necessarily like that one combustion is not part of the control. So, because it's showing the compression stroke, it's showing
Really glad to do this.
power stroke. Showing the combustion. That's not part of the 4 stroke. All right, easily get confused with that one, but they're different.
That's 4 classes.
Oh, okay.
And then my question for you is, the only homework I'm missing in chapter 5 is worth doing.
I think so.
Okay. I'll get it
Yeah,
done.
no, that's actually one of the big ones because, especially with the
spreadsheet and everything.
Just, yeah, getting used to the spread and
Okay.
checking thing, yeah.
Double checking calculations versus spreadsheet.
That
Okay, I'll get it done.
concept.
Latest I can turn in.
Final.
Final. Perfect.
I'm opening this through this, but the brain is telling me that it's going to be very different. It's going to be different stationary problems. Like we're just looking back and forth.
No,
So,
Do you see my note? No. Perfect. I will check this and see if we did even better than last time.
Oh, you
I found it.
Okay.
It was stuck in the middle of a bunch of labs from the other class. And it was like stuck because I checked for it. It was stuck on the back. And you got to two there.
Okay,
Well,
so you're
since I know you did the efforts, see if you can do better. Hello, Hazel.
More questions?
break it to X and Y. Yeah, that's really easy. Just break it to X and tilt it this way, and then
Oh, come on.
now it's this way. X and Y. Yeah. Okay, so once you've done this, right, it's X and Y. Now you've got force going like this, and force going like this. Now you take away everything else except for this little plasma, and then all you've got is spreadsheet butters.
No, I'm getting there.
You're not doing those forces. Tilt your shit. Put a lot of prime orientation so that now you have, you know, force.
All right.
So I was wondering if I could check my lab. So I did the 20 power.
But that's kind of neat, because you can tilt it once to get rid of these guys, and force it on the others, and then you'll tilt it again, which is why the forces you found on this.
RPM divided by the 5252, and I checked that those are right conversions.
This should be intention, it should
And then breaking power is
and I don't think it's going to
12 times, and then that was a conversion, that's why I'm 150. And I divided that by displacement. For displacement, I used the 60.6 inches cubed. I can
And
see.
you know, I don't remember it right offhand with the, you know, what the number is supposed to be on that. What are your units? Did you like you do a hand count to?
Yeah, it was
with the units?
PSI.
Yeah, okay.
I went to PSI. And then, so I got the same number, roughly the same number as Mackenzie for this one, and he used a 9931. So we got the same, but for efficiency, we got very different numbers. He got 3% or something, and I got 90.
Yeah, it's more like 93%.
Okay, so this seems about right. 90, and then it goes down to, I think, 7.
Oh, yeah, no, I'm gonna have to do it again.
Yeah, you gotta do it for
That's
this
right.
direction.
Yeah, I don't remember the numbers, but it was something like that. That's what the curve looks like.
When you're moving it, whatever.
Yeah, and that doesn't. Yeah,
Okay, I just wanted to double check.
Force degrees is net rest, and then you have
Yep.
the station.
Good.
And in between is gonna be your highest stress area. I don't even know how to do that. I guess you would just say, hey, a range between here and here is gonna spike, so. I guess you would just do a couple that like 10